Thank you very much, Mingda, for the introduction, the opportunity to welcome folks to the APS CNM User Committee meeting. Thank you, Mingda, for the shout out. I like to the idea of let's conquer everything and let's have some fun. So looking forward really to hearing a report later this week about have we accomplished those objectives. Also wanted to say it's a good time of year to know those evacuation routes. It is the time of year when tornado warnings and those concerns can pop up on relatively short notice. So please, from a safety standpoint, please keep that in mind and be prepared to exit if you need to, if you're asked to. So let me say really welcome everyone to the APS CNM user meeting. I'm very happy to see all of you here. It's an honor really to host this meeting for the users of the Advanced Photon Source and the Center for Nanoscale Materials. We are grateful for your contributions. Today is an opportunity to discuss your current and future research, to share ideas, and to strengthen the scientific community that we build together. Through your work at the Advanced Photon Source and CNM, you help accelerate progress across many fields of science, from materials and medicine to energy and technology. Your experiments drive discoveries that improve lives, open new possibilities, and solve pressing challenges. Through your efforts, you're helping us to expand the technology frontiers that secure America and the world's scientific future. The experiments that you carry out and the collaborations that we forge together at Argonne accelerate many areas of science. Today's focus is your work and the discoveries that you've made. And I would like to take a few moments to share how Argonne's broader mission connects to and supports your work. I will start by highlighting how user research at the APS and the CNM help drive progress for our laboratory's 5 signature contributions to science and society. First, our work has long been grounded in basic discovery science, including the experiments that you conduct every day at our user facilities. Our areas of strength include materials, chemistry, physics, and applied mathematics. Second, we are developing innovative energy solutions, such as advanced nuclear energy systems and next-generation batteries. Third, we are building foundations for emerging technologies, most notably high-performance computing and AI, autonomous synthesis, quantum science, and microelectronics. Fourth, we are helping assure a secure future for the U.S., for example, in strengthening of domestic supply chains for critical materials. And last but not least, we are developing tomorrow's STEM workforce, which is essential to our mission. And I will come back to this just in a few moments. But at this time, I'd like to review Argonne's discovery science and our work in emerging technologies. Within the last several months, we have completed major upgrades to our 2 premier research facilities, the APS and the Argonne Leadership Computing Facility, which is known as the ALCF. The X-rays produced by the APS are now the brightest made by any synchrotron light source in the world. Because of that, you can see processes and structures inside materials with unprecedented detail, which empowers you to gather experimental data faster than ever before. Across campus, our new supercomputer, Aurora, is designed specifically to meet the computing needs of scientific and engineering research. It is one of the fastest supercomputers in the world, and it is also one of the computers best suited for AI-assisted computation. And at the CNM, we house some of the most advanced facilities for nanoscience research. It is at the forefront of discovery science, assisting national challenges in quantum, AI, machine learning, optoelectronics, and microelectronics. Our scientific discoveries at these facilities both expand our understanding of the world around us and lay the foundation for future technologies that benefit society. I often say that Argonne is a very special, wonderfully diverse, unique place. In fact, there is nowhere else in the world where you can find our combination of user facilities at one location. The Advanced Photon Source, the Argonne Leadership Computing Facility, and the Center for Nanoscale Materials all working together seamlessly. This suite of cutting-edge research facilities provides unmatched tools to drive progress in all fields of science and technology. They enable groundbreaking insights into the structure and dynamics of matter, from the atomic to the macro scale, as well as deep understanding of natural and engineered processes. And they allow us to do science at scale and at a remarkable speed and accurately. Not only can you perform your experiments all in one place, but you can also connect and collaborate with many different scientists from many different fields from across the world. The best way that we achieve breakthroughs for our country and the world is by working together. Something I don't need to share with this group. Multidisciplinary science and teamwork are how we unlock new scientific frontiers and advance emerging technologies of the future. That's why I'm excited to see all of you here from industry, academia, and other government agencies and the national laboratories. Together, we can share insights from one field that can spur solutions in another. By partnering with researchers with various expertise and backgrounds, we can shed new light on the many challenges that we face. Your perspectives, your knowledge, your collaboration are key as we forge new pathways ahead. With all of you, we will continue to achieve breakthroughs across the scientific community. Over the next few days, I encourage you to network, explore opportunities for collaboration, and identify areas where we can combine our strengths. I know there will be several new faces participating in this year's meeting, so take the opportunity to make new friends and colleagues, which can help transform really tomorrow. As I mentioned earlier, fostering the next generation of scientists is a major part of the laboratory's mission. That's why I'm excited to see the early career researchers are presenting their work during the poster session. We look forward to seeing what our new researchers discover and what our new researchers will discover as they progress in their career. Before I hand things off to Laurent, I wanted to express my appreciation to Andy Schwartz, who will be joining us in just a few moments. He serves as the Deputy Associate Director of Science for DOE's Office of Basic Energy Sciences. And just acknowledge that we could not really provide the equipment and the support of these user facilities without the Department of Energy's investment. Our collaborative partnership with the Basic Energy Sciences program and user communities enables remarkable breakthroughs. And we do appreciate Andy for all of his efforts and for his being such a great champion for basic energy sciences and for the national user facilities. I also want to recognize our keynote speaker, Ting Zhu of the Woodruff School of Mechanical Engineering at Georgia Tech Institute of Technology. Thank you also to DJ Akwanda of the University of Texas at Austin for being the CNM keynote, and Katrina Chapman of Stony Brook University for being the APS keynote. We appreciate your sharing your expertise and insights with all of us. Our academic partnerships are essential to helping us expand our knowledge of numerous scientific fields. And it's great to have Katrina return to the laboratory and share her research, if you will. So welcome, Katrina, especially. Lastly, I'm grateful to have Dava Kivni and Misha Zarkanov, DOE Office of Science Program Managers. Their support of the APS and CNM is crucial. Thank you again for your participation. Your work will help accelerate the science and technology that drive economic prosperity and security. I wish all of you a productive meeting. Now I'm going to turn things over to Laurent Chapon, the Associate Laboratory Director for Photon Sciences and Director of the Advanced Photon Source. So Laurent, please.
Thank you, Paul. It's a pleasure to see so many of you. And let's see if my duty right now is to introduce the next speaker, who is Andy Schwartz. Let's see if Andy is online as I introduce him. So it's really a pleasure to see so many of you joining us for this APS CNM user meeting. It's the second year in a row that we have this meeting in person since the pandemic, and I think it's really good, as you mentioned this morning, for people to brainstorm and exchange ideas and maybe think about new experiments to do in the future using both facilities. So it's my pleasure to welcome Andy Schwartz. Andy Schwartz, Dr. Schwartz is the Deputy Associate Director for Basic Energy Science in the Office of Science of the Department of Energy. Andy joined DOE in 2008, initially as a program manager, and he went on he played a key role in the Energy Frontier Research Center, the FRCs, where he was a technical advisor between 2013 and 2022. In 2022, he became the Director for Material Science Division in BS. DOE played a key part with a huge portfolio in basic research, material research, chemistry, and so on, as you know. But he's been also acting since he has multiple hats, I have to say, and has been acting for the Scientific User Facility as well as doing his role as a Deputy Associate Director. So despite the fact that Andy is wearing all these hats, he's been a fantastic support for the scattering facilities, neutrons, X-rays, and the nanocenters, and really play a key role not only in supporting the mission of DOE by, giving us the funding, but also continuing to give us guidance and support in the way we execute our mission. So he's been a very precious partner. Really enjoyed the discussion that we have with Andy, and certainly at the life source directors level, really have fantastic discussion and fantastic support. So I want to recognize Andy for that. Andy, I think if you're ready to go, I think we're ready to welcome you here on this side. The audience is here. I don't know if we can hear you.
Thanks, Laurent. Can you hear me?
Yes, we can.
Perfect. All right. So maybe I can share from this side slides if whoever is running the can stop the share on that side. Thanks, Laurent, for those words. I really appreciate that, and thanks also to Paul for the introduction. Let me start this up. Ensure that you're seeing the correct screen. Somebody can confirm. Does that look good? I probably can't hear you anymore.
Yes.
Great. Fantastic. Okay. Well, thanks again. Thanks very much, Laurent, for that very nice introduction. Let me just say that all of the feelings are mutual. We really, really appreciate all of the work that goes on at Argonne, particularly at the facilities, but also among our Argonne leadership. Paul, of course, has been a wonderful partner and champion for everything that BES does at the lab and also across the complex. And we want to thank him and all of the Argonne staff for that. So again, as Laurent noted, my name is Andy Schwartz. My primary role currently is as Deputy Associate Director, though I have also some oversight responsibilities for both the Material Sciences Division as well as the User Facility Division that operates both the APS and the CNM. I will say, I want to start actually by saying that actually I'm kind of the understudy today, and I have to apologize. First of all, we'd like to apologize for not being there in person with you. We do like to try to attend these user meetings. It's a wonderful opportunity bringing together the communities of researchers who take advantage of our facilities. Current circumstances prevented that from happening, but thanks to Argonne for allowing for this virtual presentation. I also wanted to say that I wanted to introduce to you actually our relatively new Associate Director for Basic Energy Sciences, Bindu Nair, who had a conflict this morning. Otherwise, she would be speaking in this slot instead of me. But I wanted to take this opportunity to introduce her to this community. If you haven't heard, as of roughly October of last year, Bindu joined BES, coming to us from the Department of Defense, where she was the director of the Basic Research Office at DoD for a number of years. She has a material sciences background, but actually her roles in DoD over the years have given her an incredible breadth of knowledge and expertise, scientific as well as policy and interagency coordination. So we're very excited to have Bindu on board, and again, I'm sure she will have the opportunity to get out into the communities and meet people in the coming months and years. Okay, so my role here is really just to kick this meeting off and try to make this relatively concise so that we can get to the heart of what you're here to talk about, which is all the wonderful science that's going on within at the two facilities that are the focus of this user meeting. I did want, for those of you who are not familiar, I did want to sort of give you a flavor of what is basic energy sciences and how these facilities fit into our thinking about what we are trying to achieve through the investments that we make here in BES. So the structure here is really, this is meant to show you sort of the organizational structure of BES. We have three divisions. Given that this is a user meeting, I'll start at the bottom here with the scientific user facilities. As those of you who are users know well, these are incredible resources The two facilities at Argonne are 2 of 12 facilities that Basic Energy Sciences operates across the DOE lab complex. The investments we make, of course, allow for the operation of those facilities, as well as upgrading and building of new facilities and upgrading of existing facilities. I'll say a bit about the upgrade to APS a little bit later, but leave most of that, of course, to Laurent, who is the expert. We also have a relatively small but really important accelerator and detector R&D program that is run through the user facility to ensure that there are leading edge capabilities in order to enhance and expand those facilities. Then there are 2 research divisions, the Material Sciences and Engineering Division, of which I am the current acting director, and a Chemical Sciences, Geosciences, and Biosciences Division. And I won't go into the details of those, but these really are the foundational research for across the spectrum of materials, chemistry, as well as geoscience and biosciences, through which we support research both at the universities and the national labs. All of it sort of foundational and in support of a number of cross-cutting priorities and initiatives. Obviously, this is the Department of Energy, so energy generation, conversion, transmission, storage, all aspects of the energy landscape are important, and the science that underpins those. Microelectronics and quantum information sciences are current and expected continuing priorities across the interagency, across the federal government. DOE plays a critical role in both of those areas and maybe most importantly at the intersection of those areas. And again, the science supported through these programs enables that. Criticality, as we all know, is a topic of much discussion. Understanding how we can use science and innovation to manage criticality, I think, is really what we focus on. Where can we innovate around particular critical materials through alternatives, through understanding the fundamental behavior, looking for alternatives, looking for ways to reduce the needs to get the same functionality with reduced amounts of critical materials, for example. And then cross-cutting all of that, increasing efforts around taking advantage of AI for science. And I'll say a bit about that at the very end of the talk. Okay, so this is the Department of Energy. So we have a mission, and our mission, our piece of that mission is to support the foundational science, the foundational research that underpins everything else that the department does. That's the energy missions at the department, as well as the national security missions of the department. I probably don't need to tell this to this audience because I think the audience knows this well, but everything that the department does in one way or another, I would argue, depends on materials and chemistry. And so the work that we support through Basic Energy Sciences is really foundational to achieving all of the goals that the department is tasked with covering. Obviously, I talked about the energy mission before and all the aspects of that. It's also we also think about it as sort of an integrated ecosystem. How do we support not just the people, but also the tools and the capabilities to achieve that? And that's where these facilities come in. This is a complex of national labs and user facilities at those labs that I think is unmatched, certainly with any other federal agency in the U.S. and in some sense across the globe. It's an incredible resource and a resource that enables the science and technology that the users want to do. So we think about that integrated ecosystem and how we support all the pieces of that. I talked about the core research that we support through our 2 research divisions. This is primarily a large fraction of this is single investigators and small teams of research doing that scientific discovery, the most fundamental research, grand challenge, use-inspired fundamental research. That then informs national priorities. It is informed by, but also informs national priorities in a broad range of areas, not just the energy space, but also, as I said, quantum information sciences, microelectronics, artificial intelligence, et cetera. And that feedback loop and our interaction across the interagency is incredibly important. Laurent, in his introduction, mentioned the Energy Frontier Research Centers, or EFRCs. That is one example of a number of different ways in which we support also larger multidisciplinary, multi-institutional teams of research through team science. Again, with strong connections between our core research, sort of the foundational research that then leads to these larger integrated teams, supporting and aiming to support the national priorities. So this loop really with, as you see, the arrows going in both directions is really a critical element. And then at the bottom, not to diminish it, but to indicate sort of the foundational role that the facilities play in supporting all of these activities. The light sources, the neutron sources, and the nanocenters, this complex of 12 facilities, really provide enabling capabilities that are not available, that are not available many other places in the country or around the world, and enable a level of science that couldn't be accomplished otherwise. Now, of course, we have to continue to sustain an investment to keep those. So these facilities are dynamic, as we know, and once built, they have a life cycle, and so the sustained investment in facility development, both new and upgraded facilities, is critical to make sure that they remain at the leading edge. And the way in which we do that is really to look to the community through series of reports and studies to identify where are the most impactful areas for investment in the facilities that will enable and be led by the scientific needs. And so what's shown here is a series of reports over the years on various different aspects of facilities and facility science. And what BES then does is to maintain a diverse portfolio of projects. So a significant fraction of the BES facilities division budget goes to upgrading and building, upgrading existing facilities and building new facilities. Here we show some of the current upgrades that are going on. I think this community knows well about the recent upgrade to the advanced photon source, and Laurent will speak about that a little bit later, much more eloquently and in much more detail than I could. So I'll leave that to him. There is also an active effort going on to recapitalize the 5 nanoscale science research centers, including CNM, with new instruments, and I have a couple of slides on those coming up. And then some additional, for awareness, there's just coming to completion an upgrade to the proton power source at the spallation neutron source at Oak Ridge. This is the proton accelerator that drives the target. So this allows for higher energy driving of the current target station, and also sets up for the development of the so-called second target station at Oak Ridge. We're also undergoing a high energy upgrade to the LINAC coherent light source, or LCLS, at SLAC. Instrumentation additions, new tools, new beamlines through the next 2 and next 3 projects at NSLS2 at Brookhaven, and a major upgrade to the advanced light source, ALS, at Lawrence Berkeley National Lab. So these, along with other investments, are really intended to keep this complex, again, just some of the examples shown here, keep this complex at the leading edge. So I mentioned AP. I can't get through the talk without acknowledging the incredible story of APSU. This is, as you all know, sitting right where you are now. Was turned off in, I believe, April of 2023 for a 1-year dark time, and came back up in spring and summer of 2024, and is showing incredible promise. There's some photos here, Laurent toasting the accomplishment last summer. I think this was actually, I think this was apple juice, but I'm sure he toasted with something else at a different time. This has been an incredible achievement. The project, a little bit over $800 million of investment, achieving a world record emittance. 55 of the beamlines are now coming in commissioning, including 5 of the so-called feature beamlines, the new beamlines that are being developed as part of this project. And many of these are now open to users, with more coming. And I know everyone in this, or many of the people in this audience, are very excited about this and understand probably even better than I the implications of this. And again, Laurent will speak more about this. I'll leave that to him. As I mentioned, we're also undergoing a multi-year effort to recapitalize the equipment at the 5 nanocenters, including CNM. The nanocenters, this is the user statistics over the years. They have continued to show increased growth in users ever since they opened nearly 20 years ago. All of the centers came online, if I recall, between 2006 and 2008. So they're now 20 years in, and while they have made investments in equipment over that time frame, there was a recognition a few years ago that there needed to be a targeted, coordinated effort across all of the 5 centers to install new tools for the coming years to enable the research really in these 3 key areas that are denoted here on the left. So a couple examples. We now have, since September of 2024, 4 new tools are actually already in the user program, including 2 right where you sit at CNM, dynamic STEM, and a plasma-focused ion multi-beam microscope, a tool that is a cryoplasma fib installed at CNMS at Oak Ridge, and a dual beam ion sputtering system at CINT. Additionally, 6 tools have been delivered to the centers and are to be installed and completed. And this is part of a total of 16 plus tools that are planned for this project over the coming years. So this is really a major investment in making sure that these centers have the leading edge capabilities to provide to the user community. And with that, I wanted to just show you one more slide, and it's to return to the comment I made earlier about AI, which I kind of jumped over. But as we all know, this is the artificial intelligence, machine learning, and data science more broadly are a part of the discussion, in many different areas. And most importantly for us is to think about how these new tools are going to enable transformational science. So the Office of Science, not just basic energy sciences, but we, along with the 5 other program offices within the Office of Science, held a series of roundtables in the fall, last fall, October, November of last year, targeting topical areas in which AI could, or we believe will, have dramatic effects, and thinking about how we make sure we take advantage of those most effectively. And so what you see highlighted in red is that all 6 of these topics had involvement from BES. So the BES staff and BES researchers participated in all 6 of these. Obviously, materials and chemical sciences is most directly related to the science that we support here in basic energy sciences. But I'll note at the bottom here, there was one targeted specifically at user facilities, AI, both to enable the science, but also the operations of those facilities. So these reports, or the report from these 6 roundtables, is currently under development and final editing. We hope to have it published relatively soon. There will probably be a short summary document published first, followed by the full report. So much more to come on that. And I think that the content of this report, of these roundtables, will really help us think about how we make investments in AI that are driven by the scientific needs and will drive forward the science, including the science that's done at the user facilities. And with that, I will stop. I will thank you for your attention. I'll say that I hope you have a wonderful few days at Argonne. I'm sure there's going to be lots of exciting discussions, and I encourage you to engage with your colleagues. As Laurent said, look for new opportunities to collaborate. Think about how, the ways in which these facilities have enabled, but maybe more importantly, will enable the science that you want to do. Thanks very much. I'd be happy to take questions if there's time.
Question? Do we have any questions? Andy, it looks like we have a very shy audience this morning, so there's no question yet.
Yeah,
I'm sure he will come later.
They just want to hear from you and Gary mostly, so that's fine. That makes sense to me.
Thank you very much again. Thank you, Andy.
Enjoy the meeting.
Okay, good morning, everyone. I want to start by thanking Andy for the very nice overview of DOE. I'm sure it'll be useful for us throughout the week to hear that perspective. So my name is Gary Wiederecht. I'm the Interim Director for the Center for Nanoscale Materials, and it's my pleasure to welcome you to the 2025 APS C&M Users Meeting. And we're really delighted to have such an impressive gathering of researchers here today. This meeting is not just an opportunity for us to share findings and exchange ideas. It's an opportunity to showcase all the wonderful user science enabled by APS and C&M and to foster collaboration that will drive innovation. So it's my honor to introduce our keynote speaker, Dr. Ting Zhu. Dr. Zhu is a professor at the Georgia Institute of Technology, where he holds the Carter N. Payton Jr. Distinguished Chair for Innovation in Materials Science and Metals Processing in the Woodruff School of Mechanical Engineering. His pioneering research focuses on the mechanical behavior of advanced structural and energy materials, and his work uses modeling and simulation approaches integrated with experimental characterization results to explore these materials from the nanoscale to the macro scale. And today, Dr. Zhu will be talking with us about the mechanics of extremely heterogeneous materials, delving into his group's work on how microstructural heterogeneities can significantly enhance mechanical properties of novel systems. So please join me in welcoming Dr. Zhu.
All right, good morning. It's really my honor and pleasure to give this keynote talk. First, I'd like to thank the APS C&M meeting for inviting me for this presentation. In this talk, I'll introduce our work on the mechanics of extremely heterogeneous materials. What do I mean by the materials with extreme heterogeneity? So that means this material typically contains a broad range of hierarchical microstructures with length scale from nano to micro scales. So the processing of those materials is greatly facilitated by the novel processing methods like additive manufacturing or electrodeposition. So these extremely heterogeneous materials typically exhibit very strong mechanical heterogeneities. So that means it contains very strong stress fluctuations. That's what we call the internal stresses. So actually, one of the central themes of our research is to understand these internal stresses and also what's their impact on the overall mechanical properties. We want to harness those internal stresses to push the limits of the mechanical properties. So we know for the structural materials, they often have this so-called strength and the ductility trade-off. So you can introduce very small or the nanoscale microstructure to boost the strength. On the other hand, you may sacrifice the ductility, which means that you want to stretch it to very large strain without the fracture. On the other hand, you can also bring in the complex microstructure to boost the tensile ductility, but we may sacrifice the strength. So as we know, typically the material are limited in this shaded range, but we really want to push the boundary to this new regime that is not previously attainable using the advanced processing and also the characterization and the computation modeling. So I'll show a few examples in this presentation. I'll first introduce our study of additively manufactured stainless steel. You know, the stainless steel has been used by SpaceX for their rockets to Mars, and also we use the stainless steel in our kitchen. Then I'll further introduce the additively manufactured dual-phase eutectic entropy alloys that also give us even better mechanical properties. To understand the fundamentals of structural and stress heterogeneities, I'll introduce this fundamental research for modeled system with gradient nanotwin structures. Then I'll further introduce the recent science paper where we harness the gradient microstructure to enable the long-term structural stability and with a very good so-called resistance to the cyclic creep deformation. So in the end, I will also introduce our fundamental study of nanoscale and atomic scale heterogeneities in high-entropy alloys and also the in situ TM experiment. So as I mentioned, we really want to integrate the advanced material processing, advanced material characterization like in APS, synchrotron X-ray, neutron diffraction, and also TM to understand the spatial temporal evolution of the microstructure evolution and also with the help of the computation modeling. So let's first look at the AM stainless steel. We have been using powder bed fusion selective laser melting technology to print metal alloys. You know, this kind of very high energy, strong energy laser beam will inject the energy to the system. It will produce large temperature gradients and high cooling rates. So those extreme printing conditions produce the new opportunities and also challenges for us in both the fundamental science and engineering applications. So we have been using or have been integrating the experiment and modeling to understand the processing structure and the property relationship of AM metal alloys. So we first studied this AM stainless steel about 10 years ago. So this work has about now 3,000 citations. So you can see when we print the stainless steel at the micron scale in this EBSD map, we can see highly distorted grain microstructures. And within the micron sized grains, we observe the formation of the chemical cell structure in as printed materials. So the typical chemical cell structure has length scale about size about 100 nanometers, half micron. White layers are this chemical cell walls with a thickness about 100 nanometer. So they are enriched by the moly and the chromium. More interestingly, and those chemical cells actually can trap dislocations in as printed sample. So we know and the dislocations cells can refine the microstructure and leading to an excellent combination of high strength and high ductility. In this tensile stress strain curve of AM stainless steel, we have a very high yield strength. We also have a very good tensile strain, so-called tensile ductility. So different curves correspond to the stress strain response from different printing machines. So their strength and ductility combinations are much better than the reference strength and ductility from conventional stainless steel, from casting or wrought. So here we put the strength and ductility combination of our AM stainless steel on this diagram, and it's outside the conventional regime. So how do we understand the formation of those unique chemical cell structure? Actually, it's due to the so-called constitutional supercooling phenomenon. It's a very general material science phenomenon, and you can see them in different fields. Actually, and people use this phenomenon to explain the formation of those giant basalt column structures. In this case, it's in Ireland. So in this phase diagram, we know, and as we cool lower the temperature of liquid melt of the alloys, and so when we touch this liquidous line, so this will have the impure phase will have a higher freezing temperature, while the more impure phase would have a lower freezing temperature. As a result, at a solid liquid interface, and so these impure atoms will be pushed away so that locally and we can have this initial freezing. That's caused this morphological instability producing this columnar cell structure. So actually, before the pandemic, I attended a conference in Hong Kong. The local organizers took us for a boat visit. So we saw those huge columnar structures. So it's also formed due to this constitutional supercooling phenomenon, certainly at a different time and land scales. While those micron-sized chemical and dislocation cell structures produce very strong stress fluctuations within the cells, across the cells. So people have classified those stress fluctuations in terms of the characteristic land scales. And at the micron or at the sample land scale, and this is a so-called type 1 internal stress or microstress. So that's not the focus of our research. We mainly focus on the type 2 intergranular and the type 3 intragranular internal stresses as schematically illustrated here. For a polycrystal sample across the grains, if you measure or compute the stress across the grains, so the black solid line represents applied constant stress or the load, while across those grains, we have the green average stress represented by those red segments. They deviate from this applied stress. So those deviations are called type 2 intergranular internal stresses. While within each individual grains, because of this, for example, the chemical cell dislocation cell structures, we also can have very strong stress fluctuations and across the cells. So those are deviations from the green level averages, and these are called type 3 intragranular internal stresses. So as you can imagine, as you bring in more heterogeneous microstructures, and you would have more fluctuations, and so they can significantly impact the mechanical behavior of materials. So also we need to recognize several important characteristics of those internal stresses. Because they are internal, so they actually have to self-equilibrate, right? So you have the positive internal stress, you must also have the negative ones to balance with the positive ones. More importantly, they are often associated with the so-called long-range directional effect that can produce this like the tension compression asymmetry is also called the Bauschinger effect, which I'll further elaborate. To understand those internal stresses, we use APS in situ synchrotron X-ray diffraction to understand this or probe the green level and also the sub-green level internal stresses. And we can measure the green level average lattice strain and further calculate the so-called stress for different green families. So as illustrated here, for set of grains at different location, but with a common orientation along the loading direction, like 100 direction with along the loading direction, we call them the 100 green family. We could also have 110 and 111 green families, right? So you measure the lattice strain of those green families. The horizontal axis is here is the applied load. Y-axis shows this lattice strain of different green families. When the load is low, we have linear anisotropic responses of different green families. As the sample enter the plastic yielding regime, so we can see this different downturn and upturn nonlinear responses. That's because of this progressive yielding of a different green family causing the load shedding and the repartitioning among these different green families. So understanding those dynamic, the progressive yielding and the nonlinear behavior of the lattice strain enable us to quantify the lattice strains at the green and the sub-green scales. So here I show you this synchrotron results for the AM stainless steel. So you might notice that even without the loading, we can have the non-zero lattice strain for certain green families. So that's because of the printing induced the residual stress that can significantly impact their behavior and in surveys. Certainly, as we apply the load, we see the direct result from synchrotron and this linear and nonlinear behavior of different green families. It's really data-rich result. We also have the lattice strings from, for example, different green families in the transverse direction, and also correlated to their overall and the tensile stress string behavior. So those are this direct result at the green scale. So now I want to briefly explain this subgreen scale and the type 3 intragranular internal stresses. So we can use this so-called composite model to understand the origin of the internal stress. We have the dislocation cell walls, as schematically shown here. They have high dislocation densities. You can consider them as a hard region, while within the cell interior, we have low dislocation densities, and those are the soft region. So essentially, it's a composite with hard and soft faces. But more importantly, as you string this composite, the deformation compatibility between hard and soft faces requires the generation of geometrically necessary dislocations. In case you are not in the field, you might understand those geometrically necessary dislocations as positive and negative charges, right? So if you have a group of positive charges, they actually will collectively produce the directional field. In this case, and the directional stress field, that's what we call the back stress. And then the local and the dislocations also serve as obstacles and obstructing the dislocations. They produce the so-called effective stress. So as a result, we can partition the total stress into the directional back stress and also the non-directional effective stress. So this partition allows us to understand the contribution of different components and to the stress, and also their interaction or their synergistic effect. So on one hand, we want to understand the spatial distribution of those internal stresses. Certainly, we want to also quantitatively evaluate their impact on the overall mechanical behavior, right? So in this tensile stress strain curve for the polycrystal sample, actually, we can measure the collective back stress through this unloading branches. We did a periodic unloading to determine the so-called reverse yield point to evaluate this back stress. So if there's no back stress, you would get the asymmetric yield stress when you put the sample, when you compress the sample. However, if we have a very strong back stress effect, like the group of positive charge effect, then we will have this very strong asymmetry. So that's called the Bauschinger effect. It's a manifestation of this strong internal stress effect. So we use the crystal plasticity finite element model to account for those type 2 intergranular internal stress, type 3 intragranular internal stresses to quantitatively predict their, for example, the lattice strain responses for different green families. So here you can see, and the solid lines are the synchrotron X-ray result from APS, and the dashed lines are our crystal plasticity finite element simulations. We can well capture this residual stress effect. Without the loading and internal stress are called the residual stress. We can also follow their or predict their evolution with the loading for this behavior response along the loading direction, along the transverse direction. We can also further predict the tension compression asymmetry. We are not satisfied with just this prediction of the mechanical behavior at the sample level. We also used this spatially resolved X-ray microdiffraction in APS to measure the lattice strengths within the grains. You can see on the dark and light gray regions represent the hard and the soft regions. So we have the spatially resolved lattice strain measurement to map out the lattice string or the internal stress distribution within grains. So this enables us to understand this spatial and temporal evolution of internal stresses. So next I will further expand our scope to study a more complex system. In this case is the high-entropy alloy with eutectic microstructures. So as you can see, and the additive manufacturer produced this dual-phase nanolamellar microstructures. We have the alternating FCC and the BCC nanolayers with a typical layer thickness about 100 nanometers. While those nanolayers actually also form the micron scale the colony structures with nearly random orientations. So now we have a dual phases, right? Different from the stainless steel I just showed. We only in that case we have the chemical dislocation cell structure in single FCC phase. But now we have a mixture of FCC and the BCC nanolayers, and also the micron scale colony structures. While the extreme printing condition actually enabled a very high cooling rate and a large temperature gradient, then this really pushed the limit of this attainable microstructure length scale. So you can see, and we have a very small nanolayer thickness, while the eutectic composition facilitates the formation of this alternating the dual-phase microstructures. With this unique nanoscaled microstructure, so we can also push the limit of strength and the ductility combinations. So here and in this tensile strength strain curve, different color curves correspond to the printed eutectic high-entropy alloy after different thermal heat treatments. So we have a very good combinations of high strength and high ductility. They are much better than the strength and ductility combination from the same alloy, but produced by the conventional directional solidifications. So you can see, and this strength and ductility combinations are outside this conventional regime for other the competing and eutectic alloys. So it's a dual-phase microstructure. So in this case, actually we use neutron diffraction in Oak Ridge to measure their lattice string responses of different phases, and for each phase and for different grain families. So you can see, and we have more results. And so we also need to develop this dual-phase crystal plasticity finite element model to predict this lattice string responses. More importantly, and this enables us to partition the load in the FCC and the BCC phases. As you may know, and in typical BCC nanostructures, it's easier to reach high strength because of the smaller length scale, but it's hard to achieve a good tensile ductility. While in this case, and this ductile FCC nanolayers really confine this deformation of BCC nanolayers because of this alternating structure and enable a very good combination of high strength and high ductility combination for this BCC nanolayers. So again, we also study the detailed internal stress evolution within this complex dual-phase nanostructures in the bulk samples, right? So, and one important takeaway is this back stress accounts for about 70% of the total flow stress. So the majority of the stress increase arises from the nanostructures and also the associated directional back stress effect. So recently, and we also further studied another kind of heterogeneous microstructure using the also API's synchrotron diffraction. In this case, and we print this non-weldable nickel-based alloy using a different method. It's called direct ink writing. So this enables us to print the non-weldable super alloys. And those alloys certainly produce the well-known this gamma prime microstructure. In addition, and also produce those the nanoscale and the carbides. So we use a synchrotron experiment actually can track this internal strain and or stress evolution for different phases. and also for the carbides. So carbides, on one hand, can review its own deformation behavior through the synchrotron result, and actually can also act as this embedded sensor to review the internal string evolution within the different green families. So really provides a very powerful way of characterizing and understanding this complex internal string and the stress evolutions. So next, I'll introduce a more in-depth study to understand or for quantitative understand this internal stress effect. One question is, since we have a very strong internal stresses, can we further push the limit so that we can get the extra strengthening effect that's beyond the rule of mixture, right? So you have hard and soft phases, but the result is not just following the so-called rule of mixture. In this particular case, we use electrodeposition to print or fabricate this so-called gradient nanotwined copper microstructure. So as schematically shown here, as a microstructure shown here, we have this gradient twin layer thickness in FCC copper, and we have this half period of periodic variation of twin thickness through the sample thickness. And this is 1 period, this is 2 periods, and this is 4 periods. So this precise control of the microstructure really enabled quantitative understanding of this actual strengthening effect associated with the structural gradient. So in this tensile stretching curve, we can see that as we increase the structural gradient, we can increase the stress. So this the structural gradient can cause the strength gradient, right? So the thin layers here and give us a high strength, while the thick twin layers give us this low stress. We have a strength gradient through the sample thickness. So as we apply the horizontal load, the hard region or soft region yield first, and producing larger plastic strain, while the hard region yield later produce smaller plastic strain. Now we have this so-called plastic strain gradient. So this plastic strain gradient needs to be accommodated by the geometrically necessary dislocations, like the charge of the same sign. They collectively produce this directional backstress effect. So our quantitative study shows that most of those extra strengthening effect due to the increasing structural gradient arises from this backstress strengthening effect. So we did a more systematic study and to really resolve the backstress distribution within the heterogeneous systems, right? So you have the sample level backstress effect, but also we need to recognize the spatial distribution of backstress. It evolves with load. It's highly non-trivial to quantify them. Now, and we can use the integration of computation modeling and the experiment to clearly understand the local backstress and also the gradient effect due to the neighboring RVE, the representative volume element. They produce additional and the backstress effect. So long story short, we developed the so-called the gradient model to quantitatively predict this backstress effect. And more importantly, we were able to produce this sample with a precise control of the twin thickness with a uniform microstructure and with different average twin thickness that allows us to extract one kind of backstress associated with very fine scale structural heterogeneity. In addition, we were also able to control the structural gradient so that we can further evaluate the additional strengthening effect due to this structural gradient. And when this study and also coupled with spatial mapping of the string and within the cross section, that really enable us to quantitatively evaluate these two types of strengthening effect. And then we can predict the non-uniform distribution of the stress within the sample and that evolve with the load, and also partition this contribution from different components, the local heterogeneity at the nanoscale, and the gradient structure effect across at the macro scale, so that we can understand the spatial and the temporal evolution of extra strengthening effect associated with this heterogeneous microstructure. So this enables us to further design this gradient microstructure to maximize this extra strengthening effect. So this insight or understanding is not limited to this particular model system with a gradient twin layer thickness. It can be generalized to any other kind of heterogeneous microstructure with a subgrain and heterogeneity like dislocation cell structure with a dual phase microstructure. So the key is we need to appreciate this the concept of representative volume element. If you use a large volume element, large RVE, you calibrate your model. On the other hand, if you use small RVEs, you can also calibrate your model, right? So how would you connect them and to evaluate their common features and also different effects? So that's very important to understand the extremely heterogeneous materials. So based on those understanding, recently, and we further pushed the understanding or the limits of mechanical properties of structural materials to the long-term stability, not only for this strength and ductility combinations. In this case, actually, we refine the microstructure through this cyclic torsion. So we apply the cyclic torsion actually and to introduce this gradient dislocation cell structure within the grains. In this case, it's not from the printing I introduced earlier. It's also different from the conventional method like severe plastic deformation. In this case, we just apply the gentle and many and small torsion cycles, and this enables us to produce the gradient dislocation cell structure with extreme stability. Then, as we apply the further cyclic tension compression load, and this produces very good resistance to the ratcheting or the cyclic creep. So let's first look at this microstructure. Again, it's 304 stainless steel, right? So it's a very robust and reliable material. For example, SpaceX and use it for their rocket to Mars. So as you can see, and we have the dislocation cells with the size about 300 nanometer in this case, with a gradient distribution of their size. And then we apply the cyclic loading and tensile and loading and the tension compression with a non-zero mean stress. This will produce this unidirectional accumulative strain. That's called the ratcheting strain or the cyclic creep. And without this kind of microstructure, the reference coarse grain 305, 04, and up to this number of cycles will produce about 25% of ratcheting strain. While for this gradient microstructure, and after 10 million cycles, we only have about 2% of ratcheting strain. So in this diagram, and we know, and you really want to achieve a high strength by refining the microstructure, but this refined microstructure typically has low structural stability. While on the other hand, we also want to have a really good structural stability, achieving a low ratcheting rate. So we want to move to this regime in this kind of diagram. While for this new kind of gradient dislocation cell structures, and we were able to push the limit to this excellent combination of high strength and high or low ratcheting rate, high structural stability. So we also discovered the new deformation mechanisms due to this phase transformation during the deformation from FCC to HCP phase transformation, forming the nanolamellar microstructure that was not observed in conventional 304 under the cyclic loading. And we also understand this internal stress evolution to understand to predict their ratcheting response to compare with the experimental measurement. This shows the importance of understanding this internal stresses to further push the limit of their mechanical behavior. So next, I'll go to even small length scale to understand the nanoscale and atomic scale heterogeneity. So in this case, we work on this high-entropy alloys. As you may know, and this is a very active field currently in metal alloy community. So this example is the classical and counter alloy, and with 5 equiatomic elements, and it's a single phase FCC solid solution. In our case, and we actually replace this Mn by the PD. It's still a single phase FCC solid solution, but you can see a very dramatic improvement of the yield strength. Right? So the blue curves represent the reference tensile stress strain curve from the counter alloy at the room temperature. Solid line, dashed line is at the liquid nitrogen temperature, while the red lines are our new high-entropy alloys. So at room temperature and at liquid nitrogen temperature, we have a significant increase of the strength, maintaining the very good tensile ductility. So what's the difference here? And so we first use atomic resolution and mapping to resolve the element distribution at the nanoscale. For this reference counter alloy, we got almost a uniform distribution of all 5 elements at the nanoscale. So we use this atomic resolution EDX map for the new high-entropy alloy. You see very strong the conversational fluctuation at the nanoscale. So it's a kind of understandable because PD has a very different atomic size and electron-activity compared to other elements or compared to the Mn. So that's why, and it can cause a very strong nanoscale conversational fluctuation, not only itself and also other elements, as shown by those autocorrelation analysis. And we also did a Monte Carlo simulation for this modeled ternary alloy system to directly show that, and we can produce this nanoscale conversational fluctuation, the so-called nanoscale clustering phenomenon, and the simulated TM images is consistent with the TM experimental results. And what's their impact on the mechanical behavior? So we use the in situ and the TM deformation experiment to study the deformation behavior in real time. So you can see this very dramatic, massive cross-slip out of this primary and deformation band. So this kind of behavior has not been seen in any other conventional and FCC alloys. So that's clearly showed this impact of nano clustering in these high-entropy alloys. So on this diagram of the stress is high and the length scale is small. So that can really promote a new deformation mechanisms of a cross-slip. For example, when we run the atomistic simulation, if you have an array of nanoclusters, they will block this glide of a screw dislocation in FCC alloys. We remove the perfect atoms to display this the screw dislocation. This blue ribbon represents the stacking faults, so you can see the direct cutting process. However, if you put in more and the nanoclusters, and it will greatly facilitate the so-called cross-slip. So we know cross-slip and can enhance the strengthening and the strain hardening in the early stage of plastic deformation. We also generalized the Labouche theory for this alloy strengthening effect to study this impact of nanoscale clustering. So now we can further resolve this atomic structure and heterogeneity to understand their impact on the mechanical behavior. So in this case, I want to demonstrate our in-depth study using this fundamental study through the in situ high-resolution TM experiment for bicrystal and the straining experiment. And this is FCC and the PT and bicrystal with asymmetric tilt green boundary. So we applied this shear load and to study this system through the direct high-resolution in situ TM experiment and also the atomistic simulation. So as you can see, and this in situ TM experiment allows us to directly visualize this green boundary sliding atom by atom and step by step. So in this short video, and it lasts about 20 seconds, and you can see the sliding occur across about or the sliding displacement is about 2 nanometer. So atomic spacing is about 0.2 nanometer, right? So it's the sliding occur across 10 atoms. So this is a particular asymmetric green boundaries. Even by this just a short video and a small segment of experiment, we can learn quite a bit of new physics and also obtain new understanding of atomic scale deformation process. So this reminds us about how do we understand the defect at the green boundary. In the classical textbook, we learned that to accommodate this misorientation and misfit at the asymmetric green boundary, we need the so-called this intrinsic green boundary dislocation, 2 sets of intrinsic green boundary dislocation. But this cartoon is drawn for the simple square lattice. So what are the real and intrinsic green boundary dislocations in the actual microstructure? So now we are able to clearly identify them, right? So in the fundamentals of dislocation textbook, you have an extra half plane. That means you have one dislocation core here. And when you have this lattice mismatch, and we also have this misfit dislocation. So they combine to form this pentagon structure unit. And for this kind of 2 types of intrinsic green boundary dislocations, we can also conduct the atomistic simulation to study their initial structure and also their evolution with under the load. And this kind of intrinsic green boundary dislocations can also impact for example, the sliding or the coupled sliding of the migration at the green boundary, because to produce the green boundary deformation, we need an extrinsic green boundary dislocation, as indicated by this red symbol, right? So if you want to produce this sliding the outside, you need to inject this extrinsic green boundary dislocation, gliding through this boundary and interacting with the intrinsic green boundary dislocation. And so this detailed complex processes can be now clearly resolved through those in situ experiment and also coupled with our atomistic simulation. More interestingly, and we even discovered lots of unexpected process and that go beyond what we can achieve at this stage through the direct molecular dynamics simulation. So I mentioned the existence of these pentagon units at the green boundary, and they are the intrinsic green boundary dislocations. Actually, and they can mediate the complex green boundary deformation. For example, now we can track the motion of all the atomic columns here, right? So each white spot actually represents the projection of one atomic column. So we label all this surface atoms for the right green by these red letters, capital letters. We can also label all these surface atoms or atom columns for the left green and with green letters at the beginning. So at the end of this sliding deformation, you can see the mixing of red and green letters. So what's the implication of this mixing response? So actually, it represents the transfer of atom columns from the surface of the left green to the right green. However, this occurs at only room temperature. So this is a deformation experiment at room temperature. At higher temperature and through the diffusive process, this kind of a phenomenon is expected. However, now at the room temperature, we directly observe this the mixing, the shear induced mixing. Actually, it's facilitated by the pentagon structural unit. As a result of this mixing, actually, this two surface atomic layers disappeared during this deformation process. But those atom columns didn't disappear. They actually transfer into the surface layer of the right green. So those detailed atomic processes are now can be directly visualized and understood now with this in situ capability. So without going further details, and I just want to say that, and it can significantly impact the macroscopic deformation and causing, for example, the plastic flow dominated by the green boundary, and that can also cause, for example, the creep deformation. So this kind of unexpected process is mainly driven by the very high stress at the green boundary. So in this particular case, and we can see that through also the in situ K2 camera experiment, we can capture many snapshots. So now we can directly visualize actually the climb of a green boundary dislocation under mechanical load at room temperature. This is also quite unexpected, but if you think about the high stress play a role of high temperature to promote the defect activity, so it's now quite understandable. We are not only satisfied with the observation, so through a DOE BES project, and my collaborator and I used this in situ and MEMS-based nanomechanical testing platform inside the TEM. We can quantitatively measure the stress strain behavior of ultra-fine grained metals, thin films, and so that we can measure for example, the activation volume, activation energy. This enables us to study the deformation kinetics to determine the rate controlling steps, either at the grain boundary or within the grains. And we can also use the TEM to directly visualize the deformation process and couple with the in situ, the atomistic simulation to identify the rate controlling and the mechanisms as a function of the grain size, as a function of temperature and the strain rate. So this is another line of research to push the limit of fundamental understanding of deformation mechanisms. So I didn't have time to cover many other related study by integrating the in situ TEM, in situ and the synchrotron and neutron diffraction experiment to understand the mechanical behavior of structural materials. And to summarize, I think it's really exciting time with many new opportunities to advance the characterization and understanding of chemical structural and chemical heterogeneities. So this will enable us to develop new microstructures and to push the limits and to achieve exceptional and mechanical and even multifunctional properties. So for example, in the case of mechanical properties, we really want to push the limits of a combination of strength, ductility, and long-term stability. Finally, I'd like to acknowledge my students and also my collaborators. Thank you.
Questions for the speaker? Sure. Thank you for your talk. I was wondering what spectroscopy was used for your in situ visualization of the grain boundary sludge.
We use TEM, high resolution TEM. So what's your more specific question?
No, I was just interested in that visualization to be able to do that in situ.
Yes, in situ high resolution TEM. Certainly, we also need to have a controlled mechanical loading. Yes. Also, it's very important to be able to fabricate this bicrystal sample so that their zoom axis, 110 zoom axis align with the beam. You can clearly see these atom columns on the two sides of this grain boundary.
Just a more general question. So you covered an array of materials, and we see here, at APS, obviously a lot of different materials coming in. A lot of the work you're doing is fundamental science. Can you say which materials you see as sort of being able to scale up in the future? Which are most feasible out of all these, and to retain all these, microstructural properties?
Yeah, certainly, and we want to push the limits, and also with practical applicability and scale them up. For AM metals and alloys, they are not really limited to the small scale, right? They are the bulk samples, and they can really be applied to the real applications. Certainly cost is an issue, but for certain applications and you do for defense applications, for space applications, certainly they have a very attractive features. And yeah.
I think I'm next. One of your examples showed neutron diffraction, and I was wondering, why did you choose neutrons for that particular example? Or for that system?
Not really, and sometimes we use both. We can also use a synchrotron here, and we use a neutron and in Oak Ridge. In that case, they just got the results, and they are very good. We just use them.
Okay.
Yeah.
Thank you for your talk. I have to admit, I'm really surprised at these, I think you called them Cantor alloys. I'm surprised they exist because I just would have assumed that they would have self-purified an alloy to remove any synergy properties. But my question is, it's a little off the wall. I come from a more traditional organometallic background where the community has moved from doing like single metal catalysis, even the surface side community, right? We've gone from, we have to get a perfect platinum plane to do hydrogenation, and more the community is realizing that we need to do polymetal, polynuclear compounds, single atom alloys. Our speaker last year actually was a single atom alloy scientist, and I'm looking at these Cantor alloys. I'm like, oh my God, I'd love to throw these into an NMR tube and hydrogenate some substrates and see what would happen, add oxygen. It looks like the catalytic properties might be enormous. Have you looked at any potential applications in terms of catalysis for these materials you're making, especially the Cantor alloys?
Yeah, so generally, and this idea of multi-component concentrated alloy started with, the mechanical behavior study, but they are now pretty general, right? So people also study high entropy ceramics, and not only for mechanical property, catalysis, batteries, energy applications. Yeah, it's now and it's a very general topic for many fields. Yeah, there's lots of exciting opportunities and challenges, certainly.
Thank you very much. Some beautiful dislocation microstructures there. Can you comment on the thermal stability of these structures and how well, I suppose there's then of importance for material applications at high temperatures and so on?
Sure, yes, certainly. And if you do very high temperature, long time annealing, and they will disappear. But surprisingly, actually, and they are pretty stable for certain range of temperature and annealing scheme. In the case of stainless steel, the chemical segregation really can stabilize the cell structure. And the eutectic high entropy alloy is certainly, and by nature of design, this particular composition indeed can give a very good stability. So, and also, and in the case of that dislocation, gradient dislocation cell structure is also extremely stable, yes.
Any other questions? All right, well, let's thank our speaker.
Good morning. Can you hear me okay? Yeah, it's working? Good. Well, good morning, everyone. I'm Laurent Chapon. I'm the Associate Lab Director for Photon Sciences and the Director of the APS. It's a pleasure to see so many of you back this year for this in-person meeting. It's the second year in a row that we have an in-person meeting, so I think it's a good way to exchange, and it's an exciting time despite some of the chaos that's happening sometime here and in the rest of the world. Sadly, excited to hear about the science that you have in mind and all of the exciting opportunities for new experiment and new science. So I'll talk about obviously what has happened at the APS since last year. It's been a very busy and exciting time. So I'll spend a little bit of time on that. But before I do, I want to say a big thank you to all of the people. And sorry, I'm missing also people from the CNM here, but Connie from the CNM and also our team here at the APS. This is a picture they took recently really for organizing this meeting every year. We should really give them, all of them, and people at the CNM, a big round of applause, because it's a huge amount of work to get to this stage. And of course, I want to thank the corporate sponsors, without which this meeting will be impossible to organize every year. So really a big thanks to them. It's been a very busy year at the APS. I like to start with a little bit of science. That's probably one of the very few slides that I have on science, but we were very pleased, and I'm sure some of you in the community are directly linked or indirectly connected to this particular research. This is the Nobel Prize in Chemistry 2024. We were very pleased to be associated with a third Nobel Prize in chemistry at the APS. As you know, there was one for GPCR a number of years ago. There's another one on the structure of the ribosome, and this one is a third one, and it's interesting in a number of ways. So the Nobel Prize itself, as you probably all know, is related to this AI and model that is able to predict the shape of 3D proteins from a sequence of amino acids. But sometimes the untold story, at least for the non-expert, is that, of course, these AI models are extremely data hungry, and they cannot exist without the data in the first place. And certainly, we are very proud at the APS to be the leading contributor in terms of protein structures deposited in the protein data bank. It's more than 32,000 structures deposited from the APS. We have many partners from NIH, funded by other institutions, that are doing work in this space. And 17% of the structure worldwide have been performed at the APS. Out of the 200,000 structures in the PDB, more than 32,000 have been done here. And so we are the leader in structural biology with X-rays, and we're very proud to be indirectly associated with that. I think it illustrates one of the things that is, maybe this transformation has not completely happened yet, certainly not in material science and other fields, because it's much more complex and heterogeneous in terms of the data. But I think this is probably a precursor of what we will see happening in other fields of science, where the very vast collection of data and the proper annotation of the data, which is, I guess, easier in this case, is actually leading to discovery. And that's something that I will touch on at the end. But obviously, the big elephant in the room for us here at the APS was the upgrade of the facility. I think last year during the user meeting, we were just at the very start of the commissioning. I think we were mentioning ramping up the current, and we were mentioning that we will have the first light coming back soon. And I'm pleased to report, as you all know, that we actually delivered on this promise. So this was a picture of the old storage ring with two bending magnets per cell. This is the kind of engineering drawing of the new APS hybrid multi-band achromat, which has 7 bending magnet per cell, and then a very complex and compact array of mixed function magnets that really delivers this electron beam, which is much smaller in size, but also in angular spread, in divergence compared to the old machine. And so the goal, the promised goal, was to kind of reduce this, the electron emittance in the horizontal direction from 3 nanometers down to 42 picometers. And this, of course, in turn is the reason why you get much brighter beam at the end. So this project has been in the making for more than 13 or 14 years at this point. So it's a big deal. And we had a pretty aggressive schedule, as you remember, 1 year dark time, and then a pretty aggressive schedule to restart beam lines. And I will show you where we are in the rest of the slide. So as Andy Schwartz mentioned this morning, eventually we got first light. This is going back to Andy's message. I do confirm indeed that the glass that I had in my hand, was showing this morning, was apple juice and not champagne, which was probably the most disappointing part of the celebration, I have to say. The very suboptimal compared to my standards. But eventually we haven't drank any champagne. Where's Vadim? Still not, despite my promise that we will drink something proper. But we need about 25,000 authorization before we can do that. So we're in the process of moving there. So yeah, it was a good day. It was a perfect day. A lot of happy faces and celebration. of course, state officials, government officials, congressmen, DOE officials to celebrate first light. And the APS is 30 years old. We celebrated 30 years not so long ago. So this was really a memorable moment in the lifetime of the facility, and certainly, hopefully for all of you in the user community, an exciting time as well. So last year we were in this phase where we were delivering some current and starting to commission the machine, demonstrate in the process some new injection mechanism like multi-bunch swap-out injection, which is pretty completely new and is really at the heart of making this beam small in the first place, or at least being able to inject in the storage ring. And very quickly after that, we had a problem with one of the septum magnets during this time, but very quickly we kind of ramped the current. And then in the summer, we spent our time, we divided our time in different periods. So during the day, we will do beamline commissioning with a current of about 50 milliamp. And then during the night, progressively, we will ramp up the current. And this, the purpose of that was to, the electron beam and the X-ray generated by the electron beam is actually helping improve the vacuum. It's essentially scraping off all the residual molecules in the vacuum system. So we had this mixed period where we were doing beamline commissioning during the day and vacuum conditioning at night. It was pretty successful and quickly ramped the current above the current from the old machine, and eventually went all the way to 200 milliamp more recently. Of course, we wanted to pretty quickly measure the emittance of the beam. We had a promise to make the beam really much brighter. As you know, there's a few fourth-generation light sources in the world, one at Max 4 in Sweden, which was the very first one to go into multi-band achromat technology. ESRF in France, Sirius in Brazil, and this one, the goal was to push the emittance further down. And this was the very first measurement, which is also a good story in its own right, because I think the measurement is beautiful, but also the gratings that were prepared were actually prepared at CNM. So in the context of the APS CNM meeting, that's a good thing. So this is a gold kind of square pattern, which is deposited on silicon nitride, and you use this grating to produce a kind of a self-image of the beam, and you move the detector further away from the grating, and you measure this kind of self-imaging effect as a function of the distance of the grating. And you see some very nice interference, which essentially enable you to measure the size of the beam, and eventually from the size and machine parameters, you can go back to the predicted, to the emittance. So this was done relatively early on, a beautiful measurement. By the time we had achieved 200 milliamp, which is the nominal current that this new machine is running at, it's twice the current of the old machine, of course, because brightness is important, but also because we, as you know, the energy of the machine has shifted down from 7 GeV to 6 GeV, so this is to ensure high brightness also at high photon energy. So this is the measurement in the horizontal plane and in the vertical plane using this grating that I quickly described. And you can see that the horizontal beam size, so this is the photon beam size this time, not the electron beam size, is about 13 micron and 10 micron in the vertical direction. In the old machine, the horizontal beam size was about 280 microns. So this is really much, much smaller, but also kind of symmetric, even though it's not perfectly symmetric because of the aspect ratio of the beam in the straight. So the measurements indicated an emittance of 33 picometers in both directions, so it's kind of round beam. And typically, this was done with a single beam line operating for the measurement. But currently, Vadim told me recently that if you look at the average position of the gap of each ondulators in the ring, we typically operate around 25 picometers emittance with round beam in conventional mode. So that's really exciting and really confirm that the machine works as expected. By the way, I like to congratulate Vadim and his team. So Vadim Sajaev is our new division director for Accelerator System Division. You can stand up, don't be shy. And I want to congratulate him and his team for all of the commissioning period. he didn't get a lot of sleep and his colleagues as well for a number of months, but now he's getting back into a rhythm of alternating work with holidays, which is great. So yeah, thank you, Vadim. Thank you, the entire team. Thank you, all of the people, of course, that work on the installation. The success of this has been also greatly impacted by the fact that the installation was so precise. I forgot the exact RMS of installation, but it's about a few tenths of microns, girder to girder and magnet to magnet around the ring, which is certainly impressive. And also very good vacuum to start with. So then we got first light, I described that, June 17. You can see our favorite Mohan here. He's always everywhere. He's in every single picture. Mohan is everywhere. And it was really an exciting time. Just a reminder that we had to touch every single beamline. Even the beamline that were not upgraded or not new beamline, we had to realign something somewhere. So we have to touch 72 beamlines in order to put the facility back into service and making sure that you can do your science. So it's a huge amount of effort, and I'd like also to congratulate all the team, Robert Winarski and all of his colleagues at Mohan, and all of the people involved in radiation shielding and health physics. It's been a huge amount of work. This is a slide from Jonathan and his team. This is how it works. So we return so the yellow here is the shielding verification. The blue is the technical commissioning. Then we enter the green, light green is scientific commissioning, where we get, some first idea of how the science is going to work, some friendly users, some very friendly users. You're always friendly. And then general user program is dark green. So we had 19 beamlines in the first run. Then they added 27 beamlines. Recently, 14 were in the latest run, were put into the user program, which brings the beamline, the capacity right now around 55 beamlines that are somewhere in the commissioning phase, from shielding verification all the way to being in the user program. And about 10 left to go, and I'll describe that in a moment. We do publish, if you're interested in more details, we do publish every week an update on this chart. It's kind of, it shows the different phases of commissioning all the way from installation all the way to restarting the user program. It breaks it down in 6 different phases. And you can check your favorite beamline where we are and contact people according to what you see on the chart. But you've seen quite a lot of the beamlines have moved right compared to the last few months. And in particular, I want to highlight the completely new feature beamlines of the project. So 8ID is here. Was the first beamline, XPCS, a completely new beamline that came into the user program. 9ID, the coherent surface scattering instrumentation beamline, has followed closely behind. We have 4ID, magnetic beamline polar, which is going to take users very soon, I believe. We have 19ID, the long beamline in situ nanoprobe. Is currently in the process, well, not now because we don't have beam, but we're in the process of demonstrating not only the brightness, but also the focus size of the beam. We have to demonstrate that we can achieve 50 nanometer beam size. This is part of the key objective of the project. And we're currently, and very soon when we restart at the end of May or beginning of June, we will do this measurement. 20, which is the high energy X-ray microscopy beamline, is following behind quite closely. And then very recently, we started the ops commissioning of 28ID. And eventually, later on this year, you will see 33 and 34, which are the 2 final, completely new, what we call feature beamlines, coming into operation as well. And I want to thank also all of the partners. We have a lot of partners at the APS, NNSA, NIH, NSF funded beamlines. And they are part of the story. We work with them closely, and hopefully we made a good job at making sure everyone has a place and has a way to restart appropriately in this last few months. So I think we're in a good place right now. So all of the machine parameters have been demonstrated, 200 milliamps of current. The threshold parameters don't mean a lot, to be honest. But the objective ones, they mean project success, but I don't think they would be acceptable as a cutting-edge facility by themselves. We want to be on this side of the graph. So 6 GeV, 200 milliamps, we demonstrated better than 42 picometers We think that when all the gaps of the undulators will be closed, will be close to 20 picometers in both plane. That's something that we will measure as we restart. The brightness measurements we're waiting some of the beamlines to demonstrate that, and the inline undulators. And we've transitioned about 3 beamlines completely to operation. 2 are on their way, and eventually we have to demonstrate at least 7 new beamlines and 9 in the future. As I said before, one of the key to the project is we've touched everything at the facility. And so we had a lot of scope in the project, which is what we call do no harm, which means making sure the beamlines that were not upgraded or not new are successful. And so a lot of them are back in the user program. All of the enhancements are back in the user program. 5 feature beamlines are in advanced commissioning, 3 of them being transferred completely to ops. And as I said, number 6, 7, and 8, and 9 will be coming in the next few months. We're starting to see, I don't have a lot of time for science, but we do start to see really exciting science coming up. We've seen a few examples recently in high pressure on HPCAD, in imaging. This is XPCS. So this is work by Yu Cao from the Material Science Division, looking at nanodomains, polar nanodomains in a relaxer ferroelectric, where the key here is to measure the fluctuation of this nanodomain as you drive the system with an increasingly fast electric field, and to see how the nanodomains respond to this kind of excitation. And you see here an image of XPCS before the APS upgrade, which with a 1 second exposure. And what you see here is the same type of material with a 1 millisecond exposure. And you can see that the contrast between the speckle is actually much better in the new image than it is in the old one. So you can start to see the gains that were promised from this upgrade, certainly in XPCS, but also starting to see improvement, major improvement, I would say, in imaging as well, and coherent diffraction imaging in particular. So this is the single point that they could collect when running at kind of just slightly below 1 hertz before the upgrade, and now they can actually map out this entire frequency response in a way that was simply not accessible before. So that's a huge improvement, and I'm sure when polar and other beamlines come along, you will see the same type of improvement, whether it's spatial resolution, speed, throughput. So really exciting. A few things that have nothing to do with science that I'd like to make sure you're aware of. We're getting more and more, I wouldn't say problem, but challenges in tracking publication from the APS. There's a lot of publications that are not necessarily entered when they should, and we want to make sure that we as a community, and certainly you as users and end users of the facility, you help us in building a comprehensive record of the research being done at the APS. And so I know it's kind of maybe not the most interesting part of the work. The experiment and the science is important, but it's very important for the future of the facility. It's very important for the future of the science that you do here. So we've now assigned, every single experiment is assigned with a DOI, which is assigned at the end of each experiment. You will receive a text, a message which tells you exactly how you need to code the experiment that you do. And you can, this text is here, and you will leave in the future, starting from now, need to list the DOI of this publication so we can track the publications that are being actually published from the user community. It's very important. We do, a lot of kind of formal reporting to DOE on the way we use the facilities, the demand, and things like that. And this is part of the important metrics when it comes to including allocating budget and seeing the impact of the facility. So please, bear with us, we'll make it as simple as possible. We're also working on an easier way to deposit your publication in the first place so that it becomes much more streamlined than it is. The other thing I want to mention, it's a little bit of a call out to the community, but as you've seen recently, of course, there's a huge of interest in AI being a key driver. I mean, quantums is big, but AI is certainly nationwide and worldwide, a huge, we've seen, with Transformers model, a huge impact on science as well. It's certainly a driving topic for the Department of Energy. We spend a lot of time at the APS and at Argonne on AI jams. We had just recently a jam with 1,500 scientists from different national labs We do jam with the APS as well to train and make sure people are involved in the discussion. The one thing that, going back to the example of AlphaFold and RosettaFold in terms of protein folding problem, the one thing that we really want to hear from you is opportunity in AI for science, using in particular the large-scale facility that we have. So you're very well aware of the APS. You may not be fully aware that on the other side of the campus, we have an exascale computer. There are 3 big exascale machines in the country. One of them is here. It's a user facility. It also takes proposal. And it's connected to the APS in a way that is very unique. We have a terabit network going from here to there. And we have the co-location of these 2 facilities is absolutely, I think, well leading. And so as part of your discussion, as you meet with your colleagues and brainstorm, I really like this for you to think about that. We're seeing a huge, I'm not talking about AI for, drawing a picture, even though this picture has been actually done by ChatGPT. I don't know, I should quote it, right? I guess I need to acknowledge that. But really, I like to hear from you and your community about opportunities and challenges that you see coming up. Clearly, what we're seeing is that if you annotate your data properly, which was not so easy, by the way, before you had AI, and you curate large collection of data, you can discover patterns in your data which was not discoverable by any other way. And so as you think about your science in your particular area, I think this is something that, as we know, is coming right, left, and center. But we, I think, need to organize as a community in the best way to be able to exploit that. So I don't have a solution or proposition of what needs to be done, but I think it has to be part of the discussion as you meet and brainstorm. So I'll leave with that, and I'll be happy to take questions.
Just one clarification on your UI. First of all, it's great to hear all this stuff's working. So, for a clarification on the DOI, is it for every experiment or for every proposal that we get a DOI? Because sometimes you have multiple visits on a single proposal.
Yeah, I think it's for a single ESAF. Is that correct?
Correct.
Okay. So for a simple experimental safety assessment form, you'll get a corresponding DOI. So which means that same proposal with multiple visits may end up with more than one DOI. But you can simply quote the multiple DOIs just in a row. Nothing very, very complicated. Yeah. But it gave us also a hand to understand, where our community is publishing, what's the impact and things like that, which is more and more important, and especially in the context of demonstrating the impact, not just the number of users, but the scientific impact of the facility. That's certainly very important. Okay, then if there's no more questions, then we go to Gary, I guess. Thank you.
All right, everyone, in the spirit of this joint APS-CNM user meeting, our next speaker is Gary Weiderek. Gary has degrees from UC Berkeley and MIT, came to Argonne in Chemical Sciences Division, and eventually became the founding group leader, founding group leader in nanophotonics at CNM. Gary has won a DOE Young Scientist Award and a PCASE Award, and has authored, according to the website, 160, or is it over 160 publications in his career, and is currently the interim director of the Center of Nanoscale Materials. So let's all thank Gary.
Let's see. Can you hear me? Yes. Okay. Well, thank you, Preston. I did not anticipate a nice introduction, so thank you. Good morning. It's a pleasure to be back with you. And as interim director of the Center for Nanoscale Materials, it's a real honor to lead a facility that, like the Advanced Photon Source, exist to serve our user community. And together, the CNM and the APS form a powerful ecosystem for innovation. And we're united by a shared commitment to provide the tools, the expertise, and the collaborative environment that allow groundbreaking science to happen. In the, let's see, forward one. So in the next 20 minutes, I'll share an update on the current state of the CNM, what we've accomplished recently, how we're evolving to meet new scientific opportunities, and what's on the horizon. From quantum materials to autonomous discovery, and from AI-driven instrumentation to emerging national priorities, the CNM is both a platform and a partner for the next generation of science. And so whether you're a longtime user or a first-time visitor, I want to thank you for being part of this community. And so let's take a look at where we are, where we're going. So the CNM is one of 5 nanoscale science research centers located at different national laboratories around the country. They are part of the nation's nanotechnology initiative, and they are co-located with other nanoscience-related user facilities such as neutron or synchrotron light sources. And the nanocenters complement each other with their instrumentation and capabilities, the different thrusts of their in-house research programs, and the technical expertise of their staff. The CNM is committed to enabling high-impact research through our open peer-reviewed user program. We also conduct in-house research with our staff to discover, understand, and exploit functional materials that can benefit not only our nation, but also the world. And from fundamental research to applied science, we're committed to empowering groundbreaking work and fostering collaboration across diverse fields. And our users are central to this mission. A brief history of the CNM is shown on this slide. Since opening for operations in FY 2007, the CNM has evolved significantly. We've gone through several expansions and additions in capabilities. For example, expanding our clean room facilities and incorporating advanced microscopy tools through the Electron Microscopy Center. We've enhanced our capabilities to support your research needs, and these upgrades reflect our commitment to providing state-of-the-art resources for nanoscience. And the most recent example is the, let's see, where's my, B, is the upgrade of the hard X-ray nanoprobe with the APS. So a current snapshot of the CNM is shown here. We host about 850 users per year. We have more than 150 user tools, including more than 30 tools that have remote capabilities. Particularly, this includes our electron microscopes, our scanning tunneling microscopes, and our computing capabilities. We have 3 calls for proposals each year that are synchronized with the APS. Next call opens in June. And access is provided at no cost to users for research that's in the public domain. And there are other ways to work with us. If you are interested in doing proprietary research, we can do that on a cost recovery basis. And there's also collaborations through joint proposals. Let's talk about some of the capabilities and upgrades in the CNM. We have a broad suite of capabilities that span synthesis, nanofabrication, characterization, and theory and modeling. And each of these areas is crucial for advancing our understanding of nanomaterials and their applications. This is a little bit more detailed list of our capabilities. We have advanced microscopy and dynamics, synthesis and nanofabrication, theory and learning with AI and machine learning, and quantum information science and quantum materials. Just a few maybe more details. As I said, we have the hard X-ray NanoPro, which is probably our premier instrument, and this is in collaboration with the APS and has been recently upgraded and we can do tychography and various microscopies. We've invested heavily in the last few years in electron microscopy and also in scanning tunneling microscopy. And another really advanced tool that was developed by our previous, or led by our previous director, Ilkay Arslan, is the ultra-fast electron microscope, and this is becoming a really productive user tool with a lot of high-impact publications. In synthesis and fabrication, we have one of the largest clean rooms in the Midwest, so we can fulfill just about any nanofabrication need. We also do wet synthesis and engineering of defects, 2D materials, and various types of nanoparticles. We can do also nanobiohybrid synthesis, and we've also invested a lot in the past few years in autonomous synthesis, particularly synthesis and processing of polymers. In theory and modeling, we have the high-performance carbon computing cluster. I want to highlight this as this is our most accessed tool in terms of the number of users. It's also our most productive tool in terms of the number of papers. About 75 papers per year cite the use of carbon. And this theory and modeling team is also developing a lot of software and applications for users. Some of the capabilities, BLAST, Fantastics, et cetera, are based on machine learning and data analysis to make it easier for our users. And finally, we've also invested in quantum information science capabilities, particularly in quantum optics and single photon counting, and in 2 different cryostats, a dilution fridge and an adiabatic demagnetization refrigerator for ultra-low temperature experiments. So I wanted to highlight the 3 ways that we generally acquire new equipment. The first and the most common is through our annual recapitalization effort. This is where we take approximately 10% of our annual operating budget and invest it in new equipment. That amounts to about $3 million per year. And we do really depend on user feedback through our annual surveys, feedback with the user executive committee, and one-on-one conversations with staff, of course. And some of the capabilities that have recently been installed are shown on the right. We have an upgraded physical property measurement system. We just acquired a second Heidelberg Mascus aligner. There was a lot of demand for that instrument, so we have a second one now that also has improved spatial resolution, and you can see some of the other tools here. And very soon we'll have some really high-end capabilities. I can remember XPS being requested by users for many years, and we'll soon have, hopefully by the end of the summer, a near ambient pressure X-ray photoelectron spectroscopy capability. And we're also getting a plasma atomic layer deposition system and upgrading the current chemical vapor deposition for diamond. Will be a new tool as well. Some of our recapitalization efforts go into improving efficiencies. I wanted to highlight the liquid helium recovery system. This is something that has been in place now for about a year and has really been a big success thanks to the efforts of many in the CNM and in our facilities team. But basically it was initiated to help improve the cost of liquid helium-based experiments and also secure the supply of liquid helium so that we can be sure to, when a user flies in, that we can actually have that tool operating no matter whether there's a liquid helium limit or not. And so it's really been successful for us. It's currently recovering at least 20 liters a day. I think both of these numbers are a little bigger now, but and nearly $200,000 in about a year. And of course, it's good for the environment as well. A second way that we acquire tools is through the generous support from DOE and the NSRC QIS equipment grants. These are 2 tools that will soon be available to users. The first one on the left is the Quantum Emitter Electron Nanomaterial Microscope, or QEEM, and it combines spectroscopies, cathodoluminescence and photoluminescence, with an advanced probe-corrected scanning TEM to perform structure function experiments in an improved manner for quantum materials. On the right is the second tool that will soon be available, the Atomic Quantum Information Surface Science, or AQUIS lab. And this uses an ultra-high vacuum scanning probe microscope that's combined with an optical microscope for single photon counting
that can do quantum spectroscopy such as D2 measurements. And finally, the third way that we acquire equipment, and Andy Schwartz mentioned it in his talk, is this project that spans all 5 NSRCs. And each NSRC is acquiring a few tools, and the CNM is acquiring these 4 tools. Tool A, B, and D are already installed in the CNM. So transmission, scanning transmission electron microscope, the DAC-STEM, a plasma FIB, and a millikelvin STM. And the third, the last tool C, I'll mention in a minute, is a transient photoelectron and cathodoluminescence spectrometer. So I wanted to highlight some of the collaborations with the Advanced Photon Source. This is really a path towards really unique user opportunities for our users. First is the hard X-ray nanoprobe. As I said, it's jointly staffed with the APS and CNM. Laurent showed these images before, but you can see the tremendous improvement for if you're doing microscopy with these advances with brightness and spatial resolution. The hard X-ray nanoprobe has also been outfitted with additional capabilities in terms of confocal photoluminescence and ZL. So this is, you can do more structure function type measurements with the hard X-ray nanoprobe. We also have an active collaboration in Rio Sax at Sector 8, where that correlates rheology and shear force properties with structure, and also has X-ray photon correlation spectroscopy capabilities. And I believe there was a publication in the last month or so, maybe just the last couple of weeks, and correlating shear force with microscopic structure in materials that appeared in PRL. The transient photoelectronic cathodoluminescence spectrometer that I mentioned on the previous slide, this is going to be installed at Sector 29. We've been working with Jessica and other team members at that sector. It will complement a current CW X-ray angle resolved photoelectron spectrometer so that we can do both time resolved measurements in this tool and then the X-ray angle resolved measurements in this tool for the same sample is the general idea. And then finally, we are collaborating with the APS on the universal proposal system. It will make it easier and more efficient for users to submit proposals. The Universal Proposal System is a collaborative multi-lab effort to provide scientific users with a streamlined single system for proposal submissions across multiple facilities. Okay, we'll talk a little bit about our user demographics and outreach. Understanding our user demographics helps us to tailor our services effectively, and with users from many different fields and institutions, we foster a vibrant community that drives innovation across disciplines. So first wanted to give a shout out to our user executive committee. They advocate for the user community very well. We meet with them periodically throughout the year, and their insights help guide our strategic growth and ensure that we meet your evolving needs. And of course, they're involved in efforts such as this, and Preston is our vice chair. So we really appreciate all of the involvement. Also wanted to give a highlight to our CNM user program. We have 3 calls per year synced with the APS. It's a very thriving program. This engagement reflects strong interest in utilizing our world-class facilities and underscores the importance of collaborative research. I wanted to also acknowledge Connie Pfeiffer, our user program manager, who does just a superb job in leading our user program office, and also Katie Teets, the coordinator. And together they can work with the users and streamline all of your experiences from start to finish, and they're there to answer any questions. So our CNM user community is robust with representation from academia and other national laboratories and industry, and also about a third of our users come from other divisions at Argonne. Shown here is the distribution between on-site and remote users. Remote users is a large growth area for us. In the last 2 years, as I said earlier, we've hosted about 850 users per year. Shown here is where users hail from across the United States. Of course, we're kind of a regional facility, so most of our users do come from Illinois and the surrounding states. But we, of course, every year draw from many other states. In FY24, we drew from 31 states in the District of Columbia. Also, we have a significant global presence. Shown here is the countries that we drew from in FY24. It's 13 countries. And global interactions foster collaborations across the world to help enrich our collective scientific knowledge. Also wanted to mention the BES User Satisfaction Survey. The feedback from the recent DOE Basic Energy Sciences Survey indicates high levels of satisfaction among users regarding services and instrumentation. We take this feedback seriously and are committed to maintaining and improving the quality of our offerings. And we encourage all users to complete the survey so we can learn from your experiences. We want to capitalize on the things that are going well and make adjustments and improvements where they may not be to better serve you. So I'll just briefly mention the CNM scientific strategy. I want to start with acknowledging our CNM Scientific Advisory Committee. We have a new chair this year, Mark Hersom from Northwestern University. And we really appreciate the input that they provide in strategic guidance for scientific directions, capabilities, et cetera. So the CNM strategy focuses on 5 themes that guide our investments and research directions. By aligning our efforts with national priorities, we aim to make impactful contributions to fields such as quantum information science, artificial intelligence and machine learning, and energy solutions, just to name a few. And I'll just quickly mention 2 recent highlights from 2024 from our staff science efforts. The first is the ultra-long coherence of an electron-charged qubit. This is something that's been in development for a few years, but in 2024, a new publication was published in Nature Physics. The idea here is that you have an electron that's deposited on a bed of frozen neon at very, very low temperatures. And underneath the bed of neon is a superconducting circuit that can trap electrons and perform functions on the electrons. And in this work, they showed significant improvements in the coherence time of the qubits up to 0.1 milliseconds, which is greater than any other charged qubit out there, and can even begin to approach that of more prevalent transmon superconducting qubits. And they also showed that 2 of these electrons, 2 qubits, could be trapped in a common resonator and could interact with each other through strong coupling. So it's a starting point for being able to provide those coupled interactions that are necessary for quantum information science type computations. The second highlight I wanted to mention was the preparation of previously inaccessible semiconductor nanocrystals. This was published in Science in 2024. This was led by Dmitry Talipin at the University of Chicago. I believe he'll be speaking tomorrow. He has a joint appointment at the CNM, and other staff in the CNM were also involved, but it basically took a unique approach to the types of solvents used, particularly using molten inorganic salt solvents to prepare colloidally, some very important semiconductor materials such as gallium arsenide colloidally. And it was the first time this was able to be done, so it's quite a significant result. And there were characterization efforts performed in the CNM as well. So for the remainder of the meeting, I want to encourage you to engage actively in discussions, attend workshops, and network with fellow researchers. And together we can explore new ideas and forge collaborations that will shape the future of nanoscale science. These are some of the activities of CNM related speakers, keynote speakers, and also the joint APS CNM workshops that will be ongoing. So before I close, I'd like to express my gratitude for your participation and contributions to the CNM and the APS communities. Your innovative research and collaborations are at the heart of what makes Argonne's user facilities a beacon of transformative science. We're pushing the boundaries of both fundamental and applied research and driving enhancements that have the potential to change the world. And I thank you for your dedication and being an integral part of our scientific community, and I look forward to a fruitful meeting. And just want to conclude by inviting you to visit the vendors in the atrium and the lower gallery. And after lunch, we'll reconvene back here for the user science plenary session. And thank you for your attention. I'm happy to answer any questions.
Thank you. Tony Rowett from Carnegie Mellon. Thank you very much for an exciting talk about the capabilities and discoveries. I was wondering if you could comment on what I like to call materials maturation, what's coming out of the nanomaterials area and getting into actual applications.
So there's some of the areas that have been particularly productive have been in the low friction area. We've had discoveries in nanomaterials with ultra low friction. So it's called superlubricity essentially. And so there's been quite a bit of interest there in terms of intellectual property and joint projects. On I would say the other area where we've had a lot of interest from companies is in the AI area. There's multiple joint grants exploring different opportunities in that space. So those are probably the two biggest ones I can think of coming out of the CNM right now.
Thank you.
Okay, let's see the vendors. Thank you.